Hello, and welcome back. This is Dr. Gardner at the University of Montana, and today we're going to introduce the partial differential equation that we will continue to work with and manipulate as part of this course. And that is the groundwater flow equation. So we're going to derive the groundwater flow equation for the simplest type of aquifer and get you thinking about conservation of mass in the subsurface and how we use that to end up with a partial differential equation that's useful and something that we work with a lot as groundwater hydrologists. So to do this, we're going to combine pretty much everything that we've discussed before. So porous media, fluid energetics, discharge and Darcy's law, and storage. We're going to combine those all into and create an equation that allows us to model or predict how groundwater head changes in a system spatially and with time. So we're going to start off with conservation of mass. So there's just a few things you get to count on in this world, and conservation of mass is one of those. So we're gonna start off with conservation of mass in the subsurface, and in particular in a REV of porous media. So So we're gonna start off by thinking about an REV, which is this magical cube of porous media. And we're going to conserve water mass in our cube. So our cube here is going to have the dimensions of delta X, delta Y, and delta Z. And remember that this is porous media, so we've got sediment grains here. And pore space between them. Okay, so here we got our porous media, and let's consider now the fact that we have some water entering this porous media, REV in the X direction. So we're going to call this Q sub X in. And then we've got water exiting the media, which is Q sub X out. And for now, let's only consider one-dimensional flow in this X direction. And we're just gonna start off just by considering this one-dimensional flow in the X direction. And we're going to start off with a really simple statement, and that says that the change in mass in our cube, so delta M ReV, this is the change in mass in water, is equal to the discharge, the volume of water coming in, minus the volume of water coming out. All right, and that's a very basic statement. We're just saying if I have more water coming in than going out, then I must be increasing the mass. And if I have more water going out than coming in, I must be decreasing the mass. All right, so let's oh, actually we've got an error here already, and that's because I tried to skip a step. So I'm gonna forgive me, erase some stuff. You're gonna have to erase it too. The change in mass in is equal to the difference in the mass coming in minus the mass rate going out. All right. And we can write that in terms of discharge, because the discharge, remember, is a volumetric flux, or volumetric, the volume per time, as the rho water times Q in minus rho water times Q out. All right, so this is our initial conservation of mass. Statement here. All right. So we're going to start off here. And the next move is to say, well, okay, the discharge in minus the discharge out multiplied by the density. Now, in order to calculate or know the discharge in or discharge out, then I have to know the area across which it's occurring, or I could just normalize by that area. And so the other way to write this is this is equal to rho water times Q sub X in, all right, where this is the flux or discharge per unit area, and then I just multiply it by the area, all right, across which it's flowing. So delta Y times delta Z. Minus rho water Q X out times delta Y times delta Z. All right. Now we've got the change in mass in my ReV is equal to the density times the flux in times the area minus the density times the flux out times the area. And the trick here, the whole trick to deriving any of these continuity equations is writing my flux out as a function of my flux in. And we're going to do that by saying that Q sub x O is equal to whatever came in, Q sub x in, plus the change in Q sub x, the rate of change of Q sub x with respect to the x direction, right, times delta x. All right, so the rate of change times the distance which it's traveled would give me the change in flux, delta Q. So we're just saying, well, Q sub XO is equal to whatever came in plus the change in Q as it flowed across this delta X. So we can insert, we'll call this guy star. We can insert star in here, and we're going to end up with delta M REV is equal to rho water Q X in delta X delta Y minus minus rho water times Q X in plus dq dx delta x times delta x, or sorry, delta y times delta z. All right. Now I can do some algebra, but the trick here is that, oh, and I've got a mistake here that I'm going to fix. This is delta y, delta z. Got to have the right area. All right, so now I got I can do some algebra here, and I can easily simplify and say that the delta M REV is equal to rho water, negative rho water, dq dx, delta x, delta y, delta z. Okay. All right. So turns out I can do that for any all of my directions. So I got flow in and flow out in the z direction, and I got it in and out in the y direction. And I can just say, follow this exact same logic, and I'll end up with this statement that the change in mass in my REV is equal to rho water. I'm gonna put delta x, delta y, and delta z over here. And in here, I'll have negative dq dx minus dq dy minus dq dz. All right. Okay, so this is intermediate step 1. And it's worth probably naming this. We'll call this guy 1. All right, so now let's look at this left-hand side. What is the change in mass in the REV? Well, recall that we had an equation for the total mass of the water. In an REV, it was the so M REV is equal to the porosity of water times, or the density of water times the porosity, assuming full saturation, all right, density of water times porosity times the volume of the cube. All right. So this change in mass is the change in mass with respect to time. So this is really dm dt, and it is equal to d rho water n dt times delta x, delta y, delta z. So this is the left-hand side. All right, so this ends up being my left-hand side, so we can now set this guy equal to this guy. We can cancel out our volume of our REV, which is convenient. And now we end up with the rho water and dt is equal to negative q dx minus q dy minus dq dz. And we could further that, simplify that, because we're lazy mathematicians. We don't want to write so much as the gradient dotted in to the vector field of Q, or negative gradient dotted into the vector field of Q. And this says, this is a very important statement. We call this the continuity equation. And it says that the change in mass in our system is equal to the divergence of the vector field. All right. And really just means how is the vector, are the vectors converging at my point, in which case the mass would be increasing, or are they diverging from the point, in which case the mass would be decreasing. All right, so this is the continuity equation. We'll label it 2. I'll give it its title. And It's really just a statement of conservation of mass. But it's not entirely, it's fully correct. It's a partial differential equation. It does describe the flow of groundwater and the change in mass in the subsurface, but it is in many respects not very usable for us. It is very hard to measure the change in mass, d rho water dn. It's virtually impossible to measure the groundwater flux. And so we would really like to get this equation in terms of something that we as groundwater hydrologists can easily measure. And the trick there is that we want to get it in terms of something that's easy to measure. And that is, in particular, the easiest thing for us to measure is head. And that's the depth or the level of the water in a well, really. And so that's easy for us to measure. And fortunately, we're armed with this relationship between flux and head that will allow us to do that. So I'm going to insert Darcy's law. I'm going to use Darcy's law to get the right-hand side in terms of head. All right, so recall Darcy's Q is equal to negative K dH dx for Qx. All right, so I'm just going to insert this relationship in here. All right, and I'm going to, I got to say, again, I forgot something here. That is, I don't have my density of water. Term here. Okay, so now I'm going to insert Darcy's, and I'm going to bring the density of water over onto this other side. So we will get 1 over rho water d rho water n dt. We'll deal with this left-hand side later. And we're going to insert Darcy's in here. So this would be d dx of k dh dx plus d dy of k dh dy and d dz of k dh dz. All right, so my right-hand side is now all in terms of the gradient in head. All right, head is easy for me to measure. So now let's deal with this left-hand side. All right. So we're going to first use the product rule. So by the product rule, we can write our left-hand side 1 over rho d rho water n dt is equal to 1 over rho water times derivative of the first, second, plus second, or plus first, derivative of the second. Okay, by the chain rule. And now, again, we want to get this in terms of changes in head. So we're going to use the chain rule. And it says 1 over rho W N D rho W, oh, not M, DH, DH, DT plus rho W D N DH DH DT. Okay. So now we're getting somewhere. And the first thing we need to think about is, what does this mean, this derivative of density with respect to H? Well, think about it as really, we can start thinking about, well, what happens if I increase the height of the water column? Why would my density change? Well, I'm increasing the pressure, right? And I might compress my water a little bit. Conversely, and these H's and N's look a lot alike. Conversely, I might increase my head a little bit. I increase the fluid pressure and I might expand my porosity, right? So this change in density and change in porosity as a function of the head. Well, the head is basically, we can equate that to pressure, which we're going to do here in a sec. And all of a sudden now we're starting to think about those terms of storage that we talked about, compressibility of water and compressibility of the porous media. So in order to get head in terms of pressure, we can insert P is equal to rho water G H here. So that gives us H is equal to P over rho water G. And if we put this guy in here, then we will end up with this, d rho water dH is equal to rho water G dH dP and dN dH is equal to rho water G dn dp. All right, we can insert these guys into here and into here, and we can cancel out some row waters and some G's, and we're going to end up with, so we'll call this double star. So insert insert double star into this guy and cancel out row waters, and we're going to end up with one over row water dn row water dt is equal to n times 1 over row water d row water dp plus dn dp, and this is all times row water G. All right. 1 over row water dp. This is the fluid compressibility. So 1 over row water d row water dp. That's the fluid compressibility beta, and dn dp. This is the porous media compressibility alpha. And so we can insert these guys in here and we can get, oh, and this is all times dH dt. All right, so then we get row water G times alpha plus N beta water times dH dt. And if we recall back to our definition of specific storage, this is exactly it. So SS is equal to alpha. Sorry, I'm forgetting my row water here. G alpha plus N beta water. All right, so we can insert that here and we get down to our final left-hand side. Finally, equals to SS dH dt. Let's think about this is valid for a fully saturated confined aquifer. All right, so let's write out the full groundwater equation. SS dH dt, my left-hand side, is equal to d dx k dH dx plus d dy k dH dy plus d dz k dH dz. And this is the groundwater flow equation. This is valid for fully saturated conditions where my density does not change. Large density is roughly constant in space. All right, we've allowed for some change in density in terms of our storage term here, but it doesn't affect our fluid flow really. So our density is constant spatially. And just for the record, I did that here where I pulled raw water out of the out of this differential. So this is where I assumed that the density does not change specifically with space. All right. Okay, so fully saturated density is roughly constant spatially. And that's pretty much the main limitations on this equation. So this is our particular version of the groundwater flow equation that we just derived. It's valid for fully saturated aquifers where the density is roughly constant spatially. It is a partial differential equation written in terms of hydraulic head, which is easy for us to measure, and solutions. We'll talk all about this PDE, but solutions to this PDE will give us the head, a function of that will prescribe the head as a function of space and a function of time. As it's written right now, this is a linear partial differential equation because the parameters that control the equation, so the parameters here are things like K and SS, are not a function of the head. All right. So we call this a linear partial differential equation. It's has 3 spatial dimensions and a time dimension. There are all kinds of forms of the groundwater flow equation. We'll have a brief lecture about how we read partial differential equations and how the groundwater flow equation can be interpreted. But this is the main PDE that we'll be working with. And we'll talk about how we solve PDEs and what it means to even have a partial differential equation. Okay, thanks for tuning in, and we'll see you guys next time.